Hello again. In this video, I'm going to go over this homework problem from 4.2. So I'm just going to read through it and show you how to work it out. So it says, determine whether Rolle's theorem applies to the following function on the given interval. If so, find the point or points that are guaranteed to exist by Rolle's theorem. And of course, this is the function, and it's on this closed interval from -1 to 4. Okay, so let me show you how to do this. So first of all, this is Rolle's theorem. Rolle's theorem says, suppose that a function is continuous on the closed interval from a to b and differentiable on the open interval from a to b. Then if f of a is equal to f of b, then there exists at least one point c in the open interval from a to b for which the derivative at c is 0. Okay, so anytime you're working with a theorem, you should always, or if you're going to apply the theorem, you should always check and make sure that it satisfies all the conditions before reaching the conclusion of the theorem. So let's run through the conditions and make sure that they're satisfied first. Okay, so let's see. There's actually 3 conditions here that we need to check. All right, the first condition is the function must be continuous on the closed interval. So in this case, we have to check that this function here is continuous from on the closed interval from -1 to 4. But that's an easy argument. Polynomials are continuous everywhere from -infinity to infinity. So in particular, this of course is a polynomial, and in particular, since it's a polynomial, it's going to be continuous on any interval, namely this one from -1 to 4. So that's the argument. So since f of x is a polynomial, it is continuous on the closed interval from -1 to 4. Okay, so the second condition is we have to show that it's differentiable on the open interval from -1 to 4. And again, the argument is it's a polynomial. Polynomials are differentiable everywhere. Okay, so it's the same argument because it's a polynomial. Now remember, differentiability means that the derivative must exist. So for polynomials, derivatives exist at every point from -infinity to infinity. The big concern there is you might have functions that come to abrupt, sharp edges like this. And if that happens, the function is not differentiable at that sharp point. But for polynomials, polynomials are nice and smooth, and they never come to these sharp points. It's also possible that you could have a discontinuity, and if there's a discontinuity, it's not differentiable at the discontinuity. But again, polynomials are continuous everywhere, so you have no discontinuities. And then also you might have a vertical tangent line. Derivatives don't exist if you have a vertical tangent line at that point where you have the tangent line. But polynomials never exhibit that kind of behavior. Okay, so the end result of all this is, since it's a polynomial, it's both continuous on the closed interval from -1 to 4, and it's also differentiable on the open interval from -1 to 4. Okay, and then the third condition that needs to be satisfied is the function has to be true that f evaluated at the left endpoint has to be equal f evaluated at the right endpoint. In other words, f of a has to equal f of b. So in this case, a is the left endpoint, -1, and b is the right endpoint, which is 4. And so we're going to check and make sure that those are equal. So f of -1, we have to check and make sure that it's the same as f evaluated at 4. Okay, I'm going to do this on the calculator. So the easy way to do this on the calculator is to go to your y equals button and then enter the function into y1, which I've already done. And then after you've done that, you may want to adjust your window. Just make sure that your the range for your x values, your x min to your x max, just make sure that contains your domain. And I've gone from -5 to 5, and that contains the domain here. So that'll work. The range is harder to establish. It's hard to know what the y values are that come out of this function when you plug in numbers from -1 to 4. But if you play with it, you'll be able to figure it out. In this case, I'm going from -50 to 50, and that contains all the y values that come out of this function on this particular domain. Okay, you might want to check that by pressing graph and just seeing if it shows up with the window that you have, if the graph shows up. Okay, and in this case, this is a pretty good window for this graph. So once you've adjusted the window, then you can go to Calc, which is a second button. So you press the second button and then Calc, and then it gives you this menu, and you just want to select value. So press Enter for value, and then it will prompt you for the x value, and we want to know when x is equal to -1, so we're going to plug -1 in. Okay, so let me try this again. By the way, make sure you use the negative sign and not the subtraction sign. So -1, press Enter, and the y value is 0. So f of -1 is 0. And then let's check f of 4. So again, go to Calculate, the value, and now put in 4 for x and press Enter, and you get y is equal to 0. By the way, it's also graphing that point. 4, 0 is right there on the graph. But the important thing here is the third condition is satisfied. F evaluated at A is the same as F evaluated at B. They're both equal to 0. Okay? And so now that we've satisfied all three conditions of the theorem, then the conclusion is true. And it says there exists at least one point C in the open interval from A to B for which the derivative at C is 0. Okay, now visually, you can see on this little graph, you can see that f of A and f of B are the same, right? They're both 0. You can see that it's continuous from -1 to 4, and you can see that there's no sharp corners anywhere in between, so it's differentiable in between. So you can sort of see visually that these three conditions are satisfied. But you can also see the conclusion. The conclusion says that there must be some point in between between -1 and 4, where the derivative at that point is 0. So there's got to be a point in between here, right, and here somewhere, where the derivative is 0. Well, where is it? It looks to be about right here, somewhere down here, because the tangent line at that point is horizontal. And so the derivative at that point has to be 0. So it's whatever this point is. Okay, now we don't know exactly where that point is. We're going to find it, but you can approximate it. It's somewhere in here. Okay, but let's find it. Let's actually find the exact number. So to find it, what you're going to do is you're going to take the derivative of the original function, and then you're going to set it equal to 0. Okay, so the derivative here would be what? 3x squared minus 4x minus 7. And then you're going to set that equal to 0 to find out when the derivative is 0. Okay, so let's solve this and see when the derivative is 0. Of course, this is a quadratic, and to solve a quadratic, you have to put it in standard form, which it already is in, right? Standard form means one side is 0. And then you could either use the quadratic formula, or you could try and factor it. Now, this one is a little more difficult to factor than some of the ones that you may see in the homework, but it does factor. First of all, you know there has to be a 3x here, and then an x here. And then you know that you have two numbers here that have to multiply to -7. And so there aren't very many options. It's either 1 and -7 or -1 and +7. And so if you just play with this, you should be able to find the two that work, remembering that the middle term has to be -4x. Okay, so let's say you put -1 here and +7 here. Then the middle term in this case is not going to add up to 4x, right? You're going to get something like 21x minus 1x, so it's going to be 20x, right? So that doesn't work. But maybe if we put -7 here and +1 over here, maybe that'll work. And so let's see. You get middle term would be 3x minus 7x, which would be minus 4x. So that does work. And notice again, -7 times 1 gives you -7, right? You can check this. 3x squared, so FOIL it out, right? 3x squared plus 3x minus 7x, which gives you -4x, and then the last term would be -7. Okay, so this factors into that. And then you just want to solve this by setting each of these equal to 0. Of course, this one, x would be -1. And then this one, you add 7 over, and then divide by 3. And so you can see x is 7/3. So there's actually two places where the derivative is 0 for this function. This one down here is at 7/3, okay, which is somewhere between 2 and 3. So that's this point. But then there's this other point right here, right? The tangent line at that point has a slope of 0. So there's actually 2 points where the derivative is 0. But only one of them happens to satisfy the conclusion of Rolle's theorem, because notice it says there's at least 1 point C in the open interval from A to B. So -1 is not in the open interval. It's in the closed interval, okay, but only 7/3 is in the open interval, right? It's in this open interval from -1 to 4. So this one is not the one we're looking for. It's actually this one. Okay. Now, I'm not saying there can't be more than 1 point. There could be more than 1 point in the interval. But in this particular case, there's only one, and that's actually in the open interval from -1 to 4, and it's 7/3. Okay. Now, just to note, if this interval went from like -2 to 4, and you extended it all the way over here, then this still satisfies the conditions for Rolle's theorem, right? All three of these conditions are satisfied. And so the conclusion would still be reached. And there would actually be 2 points at which the derivative is 0 that are also within the open interval. So in that case, you actually would have more than 1 point where the derivative is 0 in the interval, the open interval. Okay. But in this case, this is the only one that works that's in the interval, the open interval. Okay. Okay, so let's just check real quick. If you go back to my math lab, you can see that indeed 7/3 is the point that's guaranteed to exist by Rolle's theorem. Okay, I hope you found this video helpful. I'll continue to work problems in the homework, and hopefully you'll get a chance to look at some of those videos as well. Okay, bye-bye.